Let's go ahead and continue our discussion of parametric curves here in 1.7. At the end of the last lecture, we talked about the graphing of a parametric curve that was an ellipse, and it was a parameterization that involved sines and cosines. I want to look at those a little bit more closely, and in particular, I want to look at parameterizations of this form where x is equal to some constant a times maybe the cosine of t, and y is equal to that same constant a times perhaps the sine of t. So again, you have a cosine and a sine, and what you want to start thinking about whenever you see a sine and a cosine in a parameterization is something circular. Now remember, we said that there's a very important trig identity we talked about at the end of the last lecture that says that the cosine squared of something plus the sine squared of that same thing is equal to 1. It doesn't matter what's in here as long as it's the same in both the sine and the cosine. The cosine squared of 2t plus the sine squared of 2t is also equal to 1. Again, it doesn't matter what's in the argument of your sine and cosine function as long as it's the same. When you square the cosine and square the sine of the same argument, it always is going to come out to be equal to 1. Well, what's true about this situation here? If we let x be a cosine t and y be a sine t, then you can see that x squared plus y squared is a cosine t, that quantity squared, plus a sine t, that quantity squared. Well, what is that equal to? Well, it's equal to a squared times cosine squared t plus a squared times sine squared t. If I factor an a squared out of both terms, we get a squared times a quantity of cosine squared t plus sine squared t, and that, of course, can be replaced by 1, and so we just have a squared. In other words, we have x squared plus y squared equals a squared. Well, if I just give you that equation that x squared plus y squared is a squared, you recognize that as a circle. Not only that, you recognize that as a circle with a radius of a. And you recognize that as a circle with a radius of a and a center at the origin of 0, 0. And that's exactly what it's going to be. If we look at some parametric graphs here of, say, well, let's just look at one. So we have cosine of t and sine of t. Well, you see we have a circle of radius 1. Now, if we change our coefficient on these two parametric functions, maybe to 3 and 3, well, they should give us a circle of radius 3 centered at the origin. And sure enough, there it does. What if we change it again? Well, if we do maybe 5 here and 5 here, we're going to get a circle of radius 5. Okay, now what happens if we change the argument? Well, what if we do, say, 3 cosine of 2t and 3 sine of 2t? Well, we get the exact same thing that we had before when we just had a t in the argument of sine and cosine. We just get a t and we get a circle of radius 3. The difference is that this parameterization, while it also goes around the circle, is going around twice as fast. In other words, as time goes from 0 to 2 pi, for the original function, let's look at, let's just put another one in. Look, here's 3 cosine of t and 3 sine of t. This will also be a circle of radius 3. For this one, as t goes from 0 to 2 pi, you can see that we're actually going around the circle once as t goes from 0 to 2 pi. Now, for the first one here, cosine of 2t and sine of 2t, as t goes from 0 to 2 pi, we actually go around the circle twice. And we can see that if we hide this one, and let's edit this one, and let our t value just go from 0 to pi, we're actually going to go all the way around the circle. You can see we have the exact same circle goes all the way around. If we just let t go from, say, 0 to pi over 2, well, that's only going to go halfway around the circle from 0 to pi over 2. But if you look at and that's again with 2t and 2t in our arguments. If we hide that one, go back to this one, and edit that one, and go from 0 to pi over 2, what is that going to do? That's just going to be the quarter of it. This one, if we go from 0 to pi, that'll give us the top half. If we go from 0 to 2 pi, that'll get us all the way around the circle. So these give us the same circle. The parameterization gives us the same circle, only this first parameterization takes us around the circle twice as fast as the second parameterization. So that's what happens when you change the argument in your sine and cosine. But again, as long as they're the same, that rule applies that sine squared plus cosine squared is equal to 1. Now returning here, if we do something like this, x equals 3 plus the cosine of 2t, and y is equal to, say, negative 1 plus the sine of 2t. Well, what have we done here? We've done our cosine and sine, same argument of 2t and 2t, so that gives us a circle, but we've shifted 3 in the x and negative 1 in the y. So that's going to be a circle of, radius is going to be 1 here. Why is the radius 1? Well, because we have a 1 that's a coefficient on our sine and cosine. So a circle of radius 1, but centered at 3 for x and negative 1 for y. Centered at 3, negative 1. Let's go ahead and put that in here. So 3 plus cosine 2t. We can edit this one, I think. Let's edit that one. We have 3 plus cosine of 2t, and then we had negative 1 plus sine of 2t. And let's go ahead and go from 0 to pi will take us all the way around the circle. And there it is. It's a circle of radius 1 with the center at 3, negative 1. Circle of radius 1. If we change the coefficients, like say we did 3 plus 2 cosine 2t and negative 1 plus 2 sine 2t, well, that's just a circle of radius 2. Centered at 3, negative 1. And the same thing would apply if we change the coefficient on the variable in the argument of the sine and cosine. As long as they're the same, we'll have a circle, but that'll just tell us, change how fast we're going around that circle. Remember again that all of this extends from the fact that cosine squared of t plus sine squared of t is equal to 1. T or theta or whatever it happens to be. And that is the main trig identity. If you can remember this trig identity, you can get actually a lot others from that. For example, if I divide everything by cosine squared, I get another trig identity. Cosine squared over cosine squared is 1. Sine squared over cosine squared is tangent. And remember that 1 over cosine is the same as secant. So 1 plus tangent squared is secant squared, or we could say that 1 is equal to secant squared theta minus tangent squared theta. Now if you take your cosine squared theta plus sine squared theta equals 1 and divide by sine, you get sine squared theta, sine squared theta. Divide everything by sine squared theta, you get another trig identity. Cosine over sine, you remember, is cotangent. Cotangent squared theta plus 1 is equal to 1 over sine, which is cosecant. So you have cotangent squared theta plus 1 is cosecant squared theta, or 1 is equal to cosecant squared minus cotangent squared. But the main one to remember, again, is this, that cosine squared plus sine squared is 1. You can get the other two off of that. Okay, I want to do one more problem then, and that is going to be something like number 27. I want to find parametric equations to represent the line segment that goes from negative 3, 2 to 4, negative 1. As I mentioned, this is similar to number 27 out of your book, and I think you have a homework problem not unlike this as well. So graphically, what are we doing here? Well, we're looking at a line segment. Let's just get a quick sketch here. As you guys know, I'm not the best at drawing these straight lines here, but there's negative 3, 2, 4, negative 1. So we have this this line segment here, and we want to go from this point to this point. So we want to travel in this direction. Now again, you can think of this as a particle moving along this line segment with respect to time, and we might as well set it up so that at time t equals 0 we're at our starting point here, and at time t equals 1 we're at our ending point here. Well, what is that going to have to mean then? We're going to want x to be some function of t, y to be also some function of t, and again, when t is equal to 0, we want this to come out to be our x value of negative 3. When y is equal to 0, we want g of 0, our y value, to also come out to be the y coordinate at this point, which is positive 2. So we want our function, when I put t in, when I put 0 in for t, I want x to come out to be negative 3, y to be positive 2. However, when we put 1 in to our function, so at 1 second later we want to be at our ending point, we want our x value to come out to be positive 4, and we want our y value after 1 second to come out to be, let's see, what was it, negative 1. Negative 1. So what does that mean? Well, you can think of just a linear transition of x from negative 3 to positive 4, and it's traveling that distance in 1 second. So that means you can think of then that x is going to have to be my starting point of negative 3 plus, well, we wanted to go from negative 3 to positive 4 in 1 second. So that means we're going to have to travel 7 units for every 1 second for every one value of t. So x will be negative 3 plus 7t. What's y going to have to be? Well, our starting value of 2 plus, for every 1 second that travels, that t goes by, the time goes by, from t equals 0 to t equals 1, we need to decrease y by 3. So that's going to be plus a negative 3 times t, or y is just 2 minus 3t. And you can see then why those formulas in the book in 27a hold. That if parameterization from x1, y1 to x2, y2, for any parameterization of a line segment, can be given by our x will be the starting point x1 plus t times the difference between the two x's, x2 minus x1. That's what we did here to get 7. We took 4 minus a minus 3. Y then will be the starting point for y, y1 plus t times the change in the y's, y2 minus y1. That's also what we did here to get a negative 3. We took a negative 1 minus 2. Okay, I think that's about it for parameterization and parametric curves, and you'll spend some more time on these as we go through your calculus careers. If you have any questions, please let me know. What's that? You have a question already? What's the password for 1.7 homework? Oh, I'm glad you asked. The password is namiety, which means excessive or redundance. So we may be getting into some namiety if we kept going on 1.7. Namiety is your password. Good luck on the homework.